I'm going to talk about the epistemology of global spacetime structure, and all of this will be happening in the context of standard classical Lorentzian geometry. This is the plan of my talk. I will first introduce the notion of observationally indistinguishable spacetimes, then briefly discuss two global spacetime properties relevant for our understanding of black holes. And then I will ask two questions. The first is, are there observationally indistinguishable counterparts to some standard simple black hole spacetimes? And discuss some of them using various notions of observational indistinguishability. And then I will ask a second natural question, namely, so what should we care? Why should we care? What follows? And if I have the time, there will be a big digression on QFT inhabit spacetime. So this will, I will now actually start with a string of definitions, just so that we get basic concepts right. I assume we all know that spacetime is a smooth manifold with a Lorentzian metric on it, and all my metrics will just look like G. There will be no GAB subscript, because I won't be raising and lowering any indices, so this will be a clearer notation. Here's a nice notion of a global spacetime property. We say that two spacetimes are locally isometric if and only if, for each point P in the first spacetime, there is an open set O containing P, and an open set in the other spacetime, such that the restricted spacetimes, so O and G restricted to O, and O prime, G prime restricted to O prime, are isometric, and not vice versa for any P and prime. And we say that spacetime property is local if it is preserved by this notion of local isometry. In other words, spacetime property P is local if for any pair of locally isometric spacetimes, one of them has P, if and only if the other one also has P. And spacetime property is global if it is not local. Consider now the following question, and I think it's a philosophically interesting question. Imagine that you are an observer living inside some general relativistic spacetime, mg. What can you learn about global spacetime properties which hold in your spacetime? One way of approaching such questions, and it has a long philosophical tradition going back to 72, is the following. You consider the set of all possible alternative spacetimes which are compatible with the chronological paths of the observers living inside your original spacetime mg. And this can be done, this can be spelled out in a more precise way, and there are actually at least 4 different ways of spelling this out in a more precise way. I will torment you only with 2 of them. So here's the first one. We say that two spacetimes are observationally indistinguishable if and only if, for every future-directed and future-inextendable time-like curve, gamma, in the first spacetime, there is a curve, gamma prime, of the same type in the other spacetime, such that the chronological paths are isometric. And vice versa, for any future inextendable time-like curve in the other spacetime. And this definition has a very natural interpretation. Take any infinitely living observer in the first spacetime. That observer cannot distinguish between first spacetime and the second spacetime using observations confined to their chronological past. Now, it may turn out that there is only one spacetime satisfying this condition. If you're lucky, that's the case. If you're unlucky, there could be multiple other spacetimes, and perhaps they differ in some properties. And if so, well, there's a sense in which you as an observer cannot ever determine which one is yours, so to speak. But
is there any concrete example of two spacetimes that are not globally?
sure.
No?
But I will be talking about some examples in what follows, so perhaps let's go back to this if I don't answer this. But the typical example is universal covering of the Sitter spacetime. So here's a second notion. I will call it weak observational indistinguishability. So we say that two spacetimes are weakly observationally indistinguishable if and only if for any point in the first spacetime there is a corresponding point in the second spacetime such that the chronological paths are isometric. And the motivation for this notion is that, well, I don't know how about you, but I am not an infinitely long living observer. And so perhaps some more reasonable notion of an observer is called for. And well, since I make observations at a particular point here and now in spacetime, perhaps it makes sense to consider observations being made at a point. Now, the interpretation of this notion is that a finitely living observer cannot distinguish between M and M prime, although some observer living in M prime possibly could distinguish between them. Yes, because note that there is the vice versa clause of this previous definition is dropped in here. So this notion is weak in two senses. The observational indistinguishability is not a symmetric notion, and instead of talking about future inexpandable curves, we're talking about points in their chronological pasts. And finally, a property P could be preserved under weak or regular observational indistinguishability, and it is preserved if for pairs of observation indistinguishable spacetimes, property holds in one of the spacetimes if and only if it holds in the other. Now, there is a bunch of known facts about this, and actually if you go back to Malament 1977, there's a whole host of other interesting facts. But the facts which sort of motivate this talk are these two. First, consider any spacetime which is not causally bizarre. Causally bizarre means that there is a point in the spacetime such that the whole of the spacetime is in the chronological past at that point. So consider any spacetime which is not that. Then it turns out that you can prove that there exists a weakly observationally indistinguishable counterpart to that spacetime, which has the same set of local properties as the original. And moreover, you can show that if you have a spacetime which satisfies some cosmologically interesting properties, such as being isotropic, inextendable, hole-free, and globally hyperbolic, there exists a weakly observationally indistinguishable counterpart which has none of those properties. And that could be read as a form of epistemic underdetermination of the cosmological model by all possible observations confined to chronological pasts point in the original spacetime. But that is the case for any point whatsoever in that spacetime. So no matter where you decide to make your observations, you cannot rule out that you're in this conspiratorial observation indistinguishable counterpart. Okay, now black holes are, I think, sort of typically in the kind of standard textbook way, characterized by the property of having an event horizon. So, and the event horizon is defined as the boundary of the past of the future no infinity. So this notion assumes that spacetime is asymptotically flat, and then you have a conformal compactification, and in that conformal compactification you can talk about the future null infinity, which is what happens if you take all the null curves and set them arbitrarily far to the future. And so, of course, if you have a sort of standard Penrose diagram for black hole spacetime, this is your future null infinity, and the event horizon in this case is this surface. This is the boundary of the causal of the path of the future null infinity. Just all of this is the path of the future null infinity, and this is the boundary. The property of being a spacetime with an event horizon is a global property. You need to know the whole of the spacetime in order to determine whether an event horizon is there or not. Because you need to know the whole spacetime in order to determine whether a particular null curve, for instance one in here, can escape to the future null infinity or not. I really like the way Jose Senavilla puts it, so I'm going to read it. Classically, the characteristic feature of a black hole is its event horizon, the boundary of the region from where one can send signals to a faraway asymptotic external region. This event horizon is usually identified as the surface of the black hole and its area to the entropy. Unfortunately, the event horizon is essentially a global object as it depends on the whole future evolution of the spacetime. And so, I think at this stage it's very natural to ask yourselves the following two questions. One is, which of the global spacetime properties used in characterizing black hole spacetimes are preserved under various forms of observational indistinguishability? And the second is, well, even if some properties are subject to a form of underdetermination, what exactly does that imply for the interpretation of static black hole spacetimes? And so now I'm going to address this first natural question. So are there observationally indistinguishable counterparts to black hole spacetimes? And I'm going to discuss three simple examples. Well, hopefully simple examples. So first, I'm going to talk about a weakly observationally indistinguishable counterpart to the Schwarzschild black hole. Now, in the proof of this theorem, which tells you that for any spacetime which is not causally bizarre, there exists an weakly observationally indistinguishable counterpart, you get a sort of recipe, if you like, for constructing such a counterpart. And so, well, perhaps we could just take this recipe and apply it to a particular spacetime, and my particular spacetime will be this. So, in other words, this will be a 1 plus 2 subregion of the maximal extended Schwarzschild spacetime. So the recipe starts with the following two observations, which are probably true. First is that if your spacetime is not causally bizarre, then for any point in the spacetime, there's an open set disjoint with the chronological past of that point. And the second property is that, the second true statement is that for any spacetime, there is a countable set of points, Pi, such that you can cover the whole spacetime with the chronological past. Now, the main idea of the construction will be that we start with a particular spacetime that we like a lot, and construct a weakly observationally indistinguishable counterpart into which all of the chronological pasts of the appropriately chosen cover of the original spacetime can be isometrically embedded by sort of putting them on a chain. One way of intuitively imagining this construction is that here's your original spacetime, and you cover it with a bunch of light comes off some point. And in the observation indistinguishable counterpart, what you do is you sort of take the first one, take the second one, take the third one, and so on. Take the causal, take the chronological paths, sort of hang them on the chain, so to speak, and then smoothly fill the gaps in any way whatsoever. And because you have pretty much full freedom of choice as far as it is humanly possible for determining what will be space-time filler in here, you can ensure that your counterpart satisfies or violates some levels.
So in the first graph, parts of the past of the second point are also in the past of the first point, but
Yes.
not in the second one. So how do you do that? How do you fix that?
So note that they will overlap here like this,
Yeah.
but all of this will be all of this. And so the part in the overlap will also be here, and the second, no, it will be like here.
Okay, so he would
But
see,
they would
he would
be
see,
but they may
would
be
see a copy.
disjoint
They
in
would see a
the,
copy of it.
yes, yeah, yeah, exactly. Yes, so this is the chain, and you smoothly fill in the gaps, and you have a lot of freedom to do so, which is useful if you want to prove underdetermination results. And I mean, if needed, this is a spacetime. Perhaps this is not as large as it could be, but there will be at least one inextendable extension, so you can take that. And so this looks like a good relativistic spacetime. And the construction will guarantee that no matter what point from your countable cover you take, you will find a corresponding point and a corresponding set by minus in the other spacetime. Okay, so this is conceptually speaking what the recipe will give you. I can take you now briefly through the steps, if you like. I don't know if this will be useful, but let's try. So here's the recipe. You pick the set of points pi, which cover the whole spacetime in the right way. And for any I, so for any of those points, you take two copies of your original spacetime. You label the first one with I and the second with I and a prime. And what you will be doing is you will be cutting out slits in those spacetimes. And then, so the sort of general picture is that you will end up with, here's your first one with a prime, second one.
So what are the slits?
Slits are connected n-1 space-like submanifolds with boundary. And so if this were two-dimensional inclusive spacetimes, what you want to do is cut out something like this. And this. Each of these will have two slits. One of the slits will be the same as in the spacetime Q without a prime, so that you will identify them like this, and the other ones you will identify like that. And so once you have the slits, what you will do is you will glue these spacetimes together by identifying lower edges of the slits and top edges of the slits. Yes, and so once you have those appropriately chosen slits, you construct a new chain spacetime by doing them in this particular way. And because for any, well, we assume that the original spacetime can be fully covered with the chronological passes of countable set of points. It's enough to do this for a countable amount of copies of this spacetime, and so we can include all of this together, and also for any PI, its chronological path will be found somewhere in here. Oh, I should have also said that, of course, you pick, if this is your first point from the cover PI, you pick the slits in such a way that they lie in an open set, which is disjoint with the chronological past of that particular point. As soon as this guarantees you that whatever your favorite chronological past, your favorite chronological, of your favorite point from the cover is, there will be something corresponding to it in this chain of spacetimes. And you continue with this. Okay, so now what do you do in case of the Schwarzschild spacetime? Well, first you need to pick your countable cover, and so perhaps here's a good countable cover. We will alternatively be taking a point from the exterior and a point from the interior. So this is my point 1, this is my point 2, point 3, point 4, point 5, point 6, and so on. And now,
so what are you doing? You're moving to the future. Each
yeah,
point you're moving into
I'm
the
moving
future,
to the future, and
including the past of the.
Yes, but remember that I can double them, so the fact that they overlap doesn't really matter.
My concern is what's going to happen when you want to cover the singularity, the points covering the singularity. What's the succession of points that approach the singularity that will cover the whole past of the singularity?
Right. Of course, the singularity is not a point in the manifold.
No, but any point to the past of the singularity is...
like this one?
What? Get closer.
And then choose a closer point.
Sure. I mean,
No?
so I can keep them like this,
Ah.
and then like this, and so on, right? And so this will guarantee that no matter how close to the singularity you want me to get, I will find something which comes arbitrarily close to that region on the Lewis diagram.
Will we be able to cover it with only countably many points in this case?
Yeah, that's corrosion proof.
I mean,
That's actually true for any.
yeah, no, it's weird thinking about it because that's not a point in the manifold. Okay. But
Yeah. I mean, these sorts of representations are sometimes misleading. Okay, and now what you do to get the spacetime which is observationally distinguishable from Schwarzschild after slow event horizon is, well, remember that event horizon only makes sense for asymptotically flat or perhaps in general asymptotically simple spacetimes. So the only thing you need to do is you need to chain them or to strangle them on the chain in such a way that this spacetime will not satisfy any reasonable decay conditions. And if you do as I did here, so I have a point from the exterior region, a point from the interior, a point from the exterior, a point from the interior, and then strung them on the chain like this, well, this means that I will have some regions with molecular curvature, so mass distribution here, and then a point from the exterior region where it gets weaker, but then I will get another one from the interior, and so on. And this chain of spacetimes will not satisfy any reasonable decay conditions, and so this will not be asymptotically flat. However, this would be with the observation distinguishable from Schwarzschild.
I have a question.
Sure.
What if I don't use your definition of an event horizon as describing something as a black hole? Because to be honest, to me that's absolutely the most useless definition that exists for describing black holes.
That's absolutely great. This means you're like 7 slides ahead of me.
Okay.
Yeah, I should have stated at the beginning that, well, you know, of course this is work in progress, possibly with other people, so I think there's a lot of interesting open questions, and many of them have to do with alternative characterizations of black holes. And actually, the next example will be about that.
But, sorry, if I am going to interpret this in a serious way, I would then try to place myself in this story, and I would then choose a particular, you know, given this set of observations, this could be me.
Right.
And given the next set of observations that I made, I discovered that this could not be me. Me needs to be somebody else. And I will have to, at every instant, as I move along and improve the set of observations, I will have to continually change who I am in that diagram.
That's right. Yes. And also you may be in
So
a
if
situation where if you're here, you could pretty easily, possibly, determine that you're here but not in this one. But
So is this analogous to imagining there is nothing in the world and just my state of mind is changing and just changing, there is no passing of time, and I am just imagining all you know,
I don't know if it's
stuff,
analogous
and
because
every time there are no laws of physics, there is nothing happening, and I'm just, in each instant I want to understand my state of mind, and I say, that's my state of mind, and I have a particular arrangement of my neurons so that it accounts for my state of mind at every particular time.
I
Is
don't know
that
how
something
to
like that?
think about this, because in this case I know what my sets of observations is and what I am in this, and I know what
Yeah,
sort
but
of
I have to
properties
change,
I'm
but
looking
my
at,
point is that you have to change it continuously
But in-
as you move along.
There will be a point that's in the future that encompasses your entire world line. There will be a copy of that in the observationally indistinguishable counterpart as well.
Do I convert it? There is a convergence to the series?
No, there's just take a point that's in everyone's future, then your entire world line will be part of that point's chronological past. So there will be a part of this observationally indistinguishable counterpart in which your entire history is embedded.
Yeah. So imagine that you're here and now. Let's say that this is your observation, the counterpart of that point in my alternative spacetime. And now imagine you corrected some sort of observations, and all sorts of interesting things happened in your life, and all of a sudden you're inside the black hole. That's exciting. Well, for that point, it is guaranteed that there will be, by construction, that there will already be something in that space-time. And so your new knowledge is already being covered somewhere in here by construction.
I might have missed it, but is there a reason why you're indexing the points in an alternating way?
I'm indexing them in an alternating way because I want to guarantee that there will be no decent asymptotic behavior. And this, I think, is the simplest way of guaranteeing that.
I see, but
Because
if
you will have a sort of, because you may think that, well, if I first took all of these points which cover the interior of the black hole,
yeah.
and then I took all of those points which cover the exterior, then perhaps I could get some decent notion of asymptotic decay in this change spacetime. And I don't want to do that because I want my observation indistinguishable counterpart with no event horizon, so I want it to be not asymptotically flat, and this is why I alternate.
I see. So your point is there can be a weakly observationally indistinguishable spacetime without asymptotic flat.
Yes. Yes. And so that's kind of analogous to cosmological examples where you have your spacetime with isotropy and you have a counterpart which is not isotropic and so on. Yeah. And this construction will also work for other standard spacetimes. But now you may ask yourself, well, Juliusz, that's kind of cheating what you just did. Because, well, that's true, your weakly observation indistinguishable counterpart has no event horizon, because it is not asymptotically flat. But this is very indirect, and it relies on dependencies between spacetime properties. And so you could say, well, Juliusz, could you give me an observation indistinguishable counterpart, which is asymptotically flat, or perhaps asymptotically predictable if you go for Wald's solution definition of an event horizon, or perhaps has some other interesting properties, but doesn't have event horizon for kind of more direct reason rather than for the fact that it doesn't satisfy prerequisites of some particular definition. And I think a philosophically interesting way of phrasing this is that, well, perhaps positing some particular space-time property P prime, or a set of such properties, could sort of break underdetermination of my favorite particular property P, in the sense that under the assumption that P prime holds, perhaps one could show that every observation indistinguishable counterpart preserves P. So this would be kind of conditional preservation of a property by observational distinguishability. And I mean, perhaps there would be, under the some particular assumption, there would be only one observationally distinguishable counterpart, namely the original spacetime, and then that would be great. Because in this case, sort of postulating P prime would give us another property P for free, so global spacetime properties would kind of come in bundles. And perhaps you're not epistemically justified to posit your favorite set of 50 different global spacetime properties, but if you just posit 2 of them, then kind of you get the rest for free, and I think that's sort of, even if you're not epistemically justified in positing these properties, that's still better than positing 50 different ones and you get 13 for free. That's the sort of thought that goes here. And so now you may ask yourself, okay, is there a asymptotically flat observation, weakly observation, distinguishable counterpart to a given spacetime? And so I asked that question, and Eric Curiel gave me an example, which is the following. You take the 1 plus 2 into Schwarzschild, so sort of like this, and you carefully remove the set from this, and so what you do is you pick this global hyperbolics, and you pick some Cauchy slice sigma like this, and then what you do is you remove the causal past of, this is my R equals 2m surface, so you remove the J minus of that, and so you remove all of this, but intersected with the chronological future of this slice and the slice itself. So what you remove is this, and this. And so now, so this is kind of like if you took the whole of the interior minus part of the event horizon and all of the exterior up to some time, but not any farther. Okay? Now, this is a globally hyperbolic, asymptotically flat spacetime, which has no event horizon, again, for the reason that future null infinity is still defined.
Is it globally hyperbolic?
Yes, it is.
Take a point inside, take a point inside, take a point
Well,
in the inside,
in here.
yeah, farther up, and take a causal curve that would have intersected the horizon, extended backwards. Sorry.
So you mean a curve like this?
Yeah.
Yeah, okay, perhaps I should also remove something like that, just to make sure that this doesn't happen, because it's a bit Right, so if I also removed this, then that would be lower hyperbolic. Now, this is weakly observationally distinguishable from the whole Schwarzschild, right? Because for any point, this is a static spacetime, so you just time translate in the interior and the exterior, and you're good. And so, well, is this philosophically interesting? I'm going to discuss this in a second, but I think it just shows you that positing some other spacetime properties like asymptotic flatness doesn't get rid of the problem, because you can get a spacetime which satisfies that property but doesn't characterize it. And in this case, actually, weak observation and distinguishability is symmetric. So you cannot distinguish this from Schwarzschild, no Schwarzschild from this, using this weak notion. Because no matter what point in the full Schwarzschild space you take, you can find a corresponding point, so somewhere earlier in here. And we're talking about eternal Schwarzschild black hole.
Not in the interior?
Yeah, also in the interior. So take this point,
Yeah.
not this point. And this is an extendable spacetime, but so is the original 1 plus 2 Schwarzschild, so I think we're good. But perhaps this is a consequence of the high symmetry. I think this trick will work for Kerr, but this will not work for ideal spacetime, so it's limited. But I think it shows an interesting conceptual point that positive additional spacetime properties may not be enough to break underdetermination of some other spacetime properties. Now, here's what happens if you consider
I
observation.
disagree.
Sorry?
I disagree. I'm sorry. Okay.
Okay. Let's do this in the Q&A. So now let me talk briefly about observational distinguishability along future inextendable timeline curves. So now some spacetimes such as Minkowski can be fully covered using chronological paths of just one future directed inextendable timeline curve. And if so, then you cannot run this sort of constructions, and so your infinitely living long observer is in a better epistemic situation than the finitely living ones. And so you can consider a spacetime which is asymptotically flat and has an event horizon. Well, it turns out that the exterior region of that spacetime can be covered using the chronological path of a single future directed inextendable timeline curve. It's easy to see in Prandtl's diagram. And so, if you work with this notion of observational distinguishability and allow yourself asymptotic flatness, then the property of having an event horizon is preserved under observational distinguishability. Well, I can still apply the chain construction, but only to the interior of the black hole, because this is where I can start cutting slits and rearrange spacetime points. And so the underdetermination is confined to the interior of the black hole, and so I think there's no reason to be worried about this. Now, okay, so what? So far this is just a simple exercise, I think. And I think that's true, it's simple, but perhaps it's instructive. I think there are two interpretations of observationally distinguishable spacetimes. One is that these spacetimes raise serious worries about our epistemic situation, and another is that, well, they're interesting because they show which spacetime properties are dependent on each other, but their interest is more mathematical, so to speak. And so I think in the case of cosmology, I could see seriousness, because, well, we're dealing with the universe as a whole, so it's natural to think of global spacetime properties as actual properties of the universe, and so the possibility of those counterparts, I think, is a serious limitation of our epistemic situation. But in case of black hole spacetimes, properties such as asymptotic flatness are just an idealization used for representing systems which are for all practical purposes isolated. And we always imagine ourselves as observers living here at infinity, and so I think this a nice way of interpreting is that we should only be concerned with observational distinguishability along future inextendable timeline curves. And if we had underdetermination for those, then we should be seriously worried about our epistemic situation. But here the underdetermination is confined to the Curiel, and there isn't that much to worry about. But the point about weak observational indistinguishability could perhaps be understood as a kind of a possibility of idealizing the whole situation. Now, as you said, the property of having an event horizon is so useless for all practical purposes, so why even be bothered with this? There are many alternative quasi-local characterizations, and perhaps they're better, and perhaps there are no observationally distinguishable counterparts for those alternative characterizations. Interestingly, this truncated Schwarzschild spacetime, I think, although it doesn't have an event horizon in the standard sense, I think it has a future trapping horizon because it has surface foliated by closed marginally trapped surfaces. This is the surface. And it also has an apparent horizon because this is the uniquely very marginally trapped cube. That's also this piece. And this is a decent submanifold of the truncated Schwarzschild spacetime. And so perhaps occurrence of observationally distinguishable counterpart to black hole spacetimes, what this does, it really highlights a flaw in the standard definition. And perhaps it could be remedied using some other alternative definition. But I think we should be cautious here. I think this actually is an interesting open question, because some of those alternative characterizations also have unpleasant global behavior, and it's not clear at all whether they will be preserved under these sorts of constructions or not. Niels, how much more time do I have? 3 minutes. Well, 3 minutes is enough for a digression. So far, all of this was in the context of GR, but there is, I think, another potentially interesting way of limiting available observationally distinguishable counterparts. So it can be shown that some, but not all, non-global hyperbolic spacetimes are quantum compatible in the sense that they can be used as a background for Minkowski-like QFD, namely local algebras associated with global hyperbolic subsets of those spacetimes form a nice enough global algebra with the right hand properties. And if you work with this notion, it can be shown that temporal orientability is a necessary condition for quantum compatibility. Interestingly, one can also show, as Malament 77 does, that the property of being temporally orientable is not preserved under observational indistinguishability. And so it seems that we're again in this situation where we can try to limit the number of observationally distinguishable counterparts by positing some other properties. Because if we demand that all the observationally distinguishable counterparts I'm going to even care about also are nice areas for a QFD, for instance, in the sense explicated by K and others, then we may kind of delimit the range of open choices and possibly break under determination of some global spacetime properties. And so I think it would be interesting to know, I think that's a good question, which, if any, of the observationally distinguishable counterparts, the particular spacetime, are quantum compatible in this or that precise sense. And I'm not even going to try to answer this question today. Thank you.
Questions, please.
So I might have missed a detail, in which case the answer is very straightforward, or I'm asking a legitimate question. One of those two possibilities. So, in your worked through example of the clothesline construction with the extra trick of the indexing, the clothesline spacetime, so the weird one, that one is not itself a weakly asymptotically flat spacetime. Is that
Yes.
true?
Yeah.
So conceptually, by the way, that means this is a legitimate question.
Oh no.
So conceptually, I would have thought that the move was, okay, if we have independent reasons from up on high to assume a certain property is present, such as asymptotically simple or whatnot, then what we're doing is we're restricting the class of models that we take to be relevant to adjudicating these sorts of epistemic considerations, or these epistemic worries. In which case, the clothesline trick is no longer, or doesn't strike me as enough anymore. Because what we're looking for is, if by virtue of other reasons I'm already committed to this property, then can I still be in error about whether I'm in a black hole spacetime or not? Does that make sense, or am I misunderstanding the character of the underdetermination?
I'm not sure I follow that, but could you just rephrase it?
Yeah, so
So I have my original spacetime and I have my observationally distinguishable, weakly observationally distinguishable counterpart.
mhm. So I guess my question is, when I hear assume that the spacetime has property P, namely that it's asymptotically simple,
Yeah.
I take that to mean, I take this to be a stronger claim than what you've attributed to it. I take this to mean, for whatever other reasons, all spacetimes that I could possibly be in are asymptotically simple.
Right. I think that's sort of what happens in this case, because that's the situation where I think I'm willing to make a very similar move, which is well, this one has not even horizon because it's not asymptotically simple, but perhaps I should restrict myself only to counterparts which are asymptotically simple or asymptotically flat. And so this made the kind of restrict the range of possible counterparts, hopefully to perhaps just one, which is the original spacetime. And if so, then positing this additional spacetime property would rule out underdetermination of this other spacetime property.
I see.
I think that's a fair point, and I think it's valid, and I think this example that Eric gave shows that it's not obvious that these moves will work in general. And so again, one should investigate this on the basis of looking at particular properties that you like. Does that answer your question?
Yeah, thanks.
Okay, quiz. Yeah, so thanks very much. So first of all, just a question. Have you found cases of bundled global properties that are appealing? I mean, you have Eric's counterexample to one that you might have had hopes for, but do you have other positive cases that you worked out? And secondly, there's there's also
Can I answer that already?
yeah.
The answer is not yet, but this is early stage.
Okay,
so
okay,
hopefully,
good. And so then there's two other questions. One is just, there's a different way of restricting it, which is to try to, and you did this a little bit considering the case of an observer in the asymptotic region in a black hole spacetime. You could just restrict it to a class of observers who you want to have the observational indistinguishability only over those sets of observers. So I'm wondering if you've explored that a little bit more.
kind of like
Yeah, kind of like this, but you could do it more generally than that, I think.
Yeah, that's another
Okay,
great question. I think there are, like, if you're interested in global space-time structure, there's so many interesting questions.
Right.
You just start thinking about black hole space-time
Right.
properties.
the other question, if there aren't other
Just Josh in the queue, but if it's a
Yeah,
short
so the
question.
other question was, the other question was quite a bit more, was sort of more general, which is in thinking about these, I mean, in very generic terms, we often have aspects of our scientific theories that represent things in a way that's much stronger than what we actually need for the inferential purposes that we're using the theories for. So the global definition of event horizon might be convenient in certain ways, but it's actually more than you need. It's sort of useless in realistic context. So and maybe we just haven't figured out how to give the local characterization that's sort of more modest that would actually be exactly what we need. So there's a general worry that perhaps some of these claims about global space-time properties are excessive in just that sense. So then you could ask the question in a different way, which is what are the inferences we're making using the way we represent space-time? How strong do we have to make these claims about the causal structure of space-time? Where is it that those come in making claims and inferences? And then is there a different way of responding to this to say, well, you know, our formulation had properties that are much too strong given the inferential purposes that we're actually using claims about causal structure for.
Right.
So is this a thing or two things? Or
And that's a very just general comment, it's sort of different way of thinking, but
So I think quasi-local notions of horizon are an interesting case to look at.
yeah.
That seems to be precisely the case where so that's exactly the case where we had a global notion, we found it unsatisfactory on conceptual grounds, so we tried to come up with another, more controllable notion, and we have a bunch of candidates, and it's actually not clear that they're all that good, because some have no phonation, and some also do have unpleasant double character, and in general they give inequivalent answers in certain cases. And so I don't think there's a single kind of superior, obviously superior alternative clarification, alternative notion available as of now. And so that's, first of all, a philosophically interesting situation, but second of all, of course, for each of those notions, you can ask yourself, okay, is it preserved under this or that notion of observational indistinguishability, and those look like tractable problems. And I mean, it's also the issue of what your notion of horizon is supposed to do for you. If you think that, well, I should just be located at infinity, and infinity is something like 2 light years or something like that, then you will be working with another notion. And perhaps for the practical purpose you're interested in, this weird closed line construction may be just as good, and so you don't have to worry about it because all the physics that you're interested in
would still be in the
would still be in there.
No, just using the demo.
I don't have anything interesting to say apparently. So we had 2 notions of observational indistinguishability. The full one that has to do with inextendable curves, and then the weak one that has to do with just individual space-time points. And the motivation for the weak one was, hey look, we're not inextendable curves, we want a notion of epistemic underdetermination. Let's kind of relativize it to the kind of creatures that we are. But how about like a middle way where we relativize it to like extendable curves? Because I'm not simply a space-time point. I do have some extension in space-time. And is there a middle way between those 2 notions? Or does the one just collapse to the other?
So do you mean something like a curve up to a point?
Yeah, that's where I die.
I think yeah, the moment where you die, that just reduces the...
Yeah, good. So it just reduces to the...
Yeah.
Good. Thank you.
Let me just say that there are actually more than 2 notions because they may be symmetric or not symmetric. So you may want to also for any point P in this space that there is a counterpoint in this one or not. And that actually gives you 4 notions.
Sure.
Symmetric or not, and along curves or pointwise.
David, please.
You don't like my example?
No, okay, that's a technical detail, but we can talk about that later. But the actual thing that I concern is the following. Once you construct this complicated space-time in which you interpolate, putting some stuff, the energy momentum tensor, I mean, if you want this thing to satisfy something like Einstein's equations, the energy momentum tensor will have to probably be very strange in those intermediate regions. So I think, you know, a question of course, this is different from your question, but the question of simplicity and naturality and so forth should tell you, okay, you know, yes,
right.
I can imagine this very complicated and strange space-time, but I would have to assume that here, you know, some matter started, and here else some matter disappear, and here,
Yeah.
all sorts of very strange things occurring in the places in between your.
Yeah, right. That's a good point. But now that this theorem actually guarantees me that the spacetime will have the same set of local properties, and so if I think of the property of being a solution to the Einstein's equation as a local property,
But in the places that you can observe, this theorem refers to those points that you can observe. But in these interpolating regions that you put to join, if I understood correctly, you construct these things, you hang them from a roof, and then you interpolate otherwise. And it's those regions which are not covered, if I understand correctly, those are not covered by this theorem.
well, I would have to go and double look at the theorem, but I'm almost certain that this one actually may have all the same local properties everywhere as this
In
one.
the interpolating place
Even
that you
in
just put by hand.
interpolating points, yes.
I think the assumption is you can just put something in there that will still satisfy the field equations. You're right, it might have a really weird stress energy tensor, or yeah, it might not.
But there's another sense in which this may be very weird, namely, even if this is somehow nice, then the initial data set associated with this may be very weird, and may have no reasonable physical interpretation. And so I think there's actually an interesting way of thinking about this. So those models are good models if I think of like, kind of kinematic constraints posited upon the theory, but there may be known dynamics for these sorts of objects, and if there's no known dynamics, then perhaps the physical relevance is kind of limited. I think that's a fruitful way of thinking about these sorts of cases. And in particular, when these sorts of constructions are used to allegedly prove limitations to our notions of prediction or things like that, I think that's exactly the place where I say, well, okay, perhaps this is a kinematically good model, but this is not what this is really important. The important thing is, can I get the kind of dynamics which takes me from a nice spacetime to one of those weird spacetimes? That's where it becomes a relevant question.
So in other words, thinking about it rather than just in terms of topology and global causal structure, thinking about it as, you know, a solution to a set of PDEs.
Yes.
Do you have a well-formulated set of initial data that will generate? And yeah, that seems right. That yeah.
Well, that seems right, but actually, I think there may be a case where actually PDs may not help you that much. So Hans Ringström has this beautiful result, which tells you that for a cosmological model with Big Bang, then satisfying a bunch of other conditions, pretty much any closed spatial topology is compatible with what you know at a given moment of time. And so I think that may potentially be a case where there's an interesting global spacetime property, topology of the space-like section, that may be underdetermined in the fully.
And he has a stronger notion of
dynamical sense.
indistinguishability than Malament's, right? I don't remember how he defines it, but he doesn't just.
It's a tricky notion, and someone should look into it.
Yeah.
But the notion that Ringström uses doesn't obviously map into any of these notions, and so that's another place where one could complicate the whole situation even further.
I guess one final statement perhaps, or you could like this.
Let's go for lunch.
Otherwise, let's take one more time, please.